In this example, we have a RL circuit. So RL circuit is one that has resistive and inductive elements. And we have a switch in the circuit. And we are told in the problem statement that at t equals 0, the switch moves instantaneously from position A to position B. So right now we look at kind of really early times, and so the current from this source is going through the switch in position A, and then it's going to go out into the rest of the circuit. And then at t equals 0, the switch is going to change, so the current will be instead directed through this path. And so basically it's just going to kind of cycle around and around in here, and effectively what we're doing is disconnecting this current source from the rest of our circuit. Now the question asks us to calculate the voltage indicated here as V0 for times greater than 0. So basically that will be when the inductor is dissipating its energy. So the inductor will supply some energy into the circuit, and there'll be some decay transient that we need to calculate. And then the question asks us what proportion of the energy that was stored in the inductor is going to wind up being dissipated in that 4 ohm resistor. So in the beginning, the inductor will have some energy stored in it, and then we want to know out of that energy how much ends up over here. So let's talk about how we can approach a problem like this. So for part A, our strategy is going to be, firstly, we need to find the initial inductor current. So let's actually label here on our diagram a current here, we'll just call it I. So we want to find the initial inductor current I at time 0. Well, actually, I guess a little bit before that switch closes. So you sometimes see a notation where you write like a I minus, which is kind of just before 0. So some really tiny little bit before 0. So the initial inductor current. And so we'll do that as we looked at in previous videos. We'll basically analyze the circuit where we replace the inductor with a short. And that will enable us to find that current. Once we have that, we will find the inductor current I of t. So the reason why we're solving for current here is that's the expression that we get when or that's the form for the differential equation that we get when we analyze inductor circuits. So it's the inductor current is kind of the easier variable usually to actually solve for. So we'll find the inductor current. But the question asks us about voltage, so we're going to need to convert that into a voltage. So we can define on our diagram a reference node and then some node voltage, which if we call it VL, then that's the same as the voltage on the inductor. So we're going to find VL, which of course, if we already know the current, is just L di dt. And once we know VL, then we can find the output voltage, or the desired voltage V0, which is a voltage divider. By voltage divider. Because we have a known voltage here, VL, that is divided over these two resistors. So that's the strategy that we will follow in order to solve part A. Then for part B, what proportion of the energy, so how would we approach that question? Well, part B strategy, we're going to find the initial energy in the inductor. Right, and we have an equation for that from our previous video. So the energy in the inductor is 1/2 Li squared. And of course, we'll use the initial current, so the thing that we calculate up here, and we'll sub that in, and that will give us the initial energy. And then we need to find the power that is dissipated in that 4 ohm resistor. So find the power at the 4 ohm resistor. And that will be straightforward because by this point we will have already solved for the voltage. So we'll have the voltage across that resistor. And once we know the power, then we can find the total energy by integrating the power. So the energy is going to be the integral over all time, so it's integral from 0 to infinity of the power that's in that that's dissipated in that 4 ohm resistor with respect to time. So let's get in and actually solve this question. So part 1, or question A, part 1 is to find the initial current that flows in the inductor. So we're solving here part A, and we want to find I of naught. So draw the circuit at steady state for t less than 0. So under those conditions, the circuit diagram has the switch in the A position. So we have our current source flowing. So what I might do is just take my diagram and redraw it down here, and we'll just kind of simplify the drawing a little bit. So we don't have this switch part, we just have the current source kind of flowing directly in. And we replace our inductor with a short. So we have just this shorted through here. So that's simplified things actually quite a bit. We can also look a little bit further, and we realize that this 4 ohm resistor will play no role, because any current that flows through here upon reaching this branch will take the path of least resistance, which is through the short, and the 4 ohm resistor will play no role, and so we can exclude it from the circuit as well. So we're basically left with just these two branches, and we have a current divider circuit here. We have a current divider. So our current divider here, because there's only two branches, I'm looking at the 10 ohm and the 6 ohm as our two branches. There's only two branches, so we can use kind of the shortcut form. So our current here, I, and actually we're solving for I of naught at this point. This is the initial current. So our current here, I of naught, is our input current multiplied by the other resistor divided by the total resistance. So that's the little shortcut form of the current divider where there's two branches. So let me just calculate. So that's 64 divided 16 is 4 amps is the initial current. Okay, let's go back and think about what we're doing. So we've just found the initial current that flows in the inductor. The next thing is to find the transient, which will be the transient after the current switches. So I should clarify here on step 2 of my strategy, for t greater than 0 is the transient that I'm trying to solve for. So let's have a look at our circuit in the kind of after the thing switches. So after the switch moves, we redraw our circuit. After the switch moves, we have that the current will go kind of through this path here, and as we previously discussed, it's basically just going to loop around and around in here, and so there's really no contribution due to this current source anymore, so actually we can get rid of it from our circuit. And then this switch is kind of meaningless as well, so we can get rid of that from our circuit, and we're basically left with just this bit here that we are supposed to analyze with an initial condition of I of naught is equal to 4 amps. So let's go ahead and analyze this. So I need to write down an expression or write down some equations that relate the voltage and the current so that I can go and use my definition of inductor behavior. So to do that, I need to analyze this circuit, right? So I can write Kirchhoff's current law at this node. I can do a node voltage method here. So I could use mesh current, I could use node voltage, I can do whatever I like. I'm going to use the node voltage method. And the reason why I choose node voltage is that will give me kind of one equation for one unknown here. If I use mesh current, I'm going to end up with actually something a little complicated. I'll have simultaneous equations and it's going to be a little bit annoying. So node voltage will be simpler in this particular case. So use the node voltage method. Okay, so what do we have here? The currents leaving from VL going towards the left is going to be VL divided by total resistance there is 16. Then there's the current leaving through the inductor is I of t. That's one of the things I'm trying to solve for. And then the current leaving through the right-hand side is VL divided by 4, and we have that equal to 0. So let's simplify this a little bit. So I'm going to multiply both sides by 16. So that will give me VL plus 16I plus 4 VL is equal to 0. 0 times 16 is still 0. Then we can collect some like terms. So this will just give me 5 VL plus 16I is equal to 0. Now at this point I need to try and eliminate one of these variables. And the thing I haven't used yet is the definition of inductor voltage. So we know that the voltage on an inductor is L times di dt, and in this particular case L is 0.32 henries, so 0.32 times di dt. So we can substitute that one in, and this will give us 5 times 0.32 di dt plus 16I is equal to 0. So 5 times 0.32 is 1.6. So I have 1.6 di dt plus 16I is equal to 0. And I can simplify that a little bit more. Di dt, just basically divide through by 1.6, so 16 divided 1.6 is 10, plus 10I is equal to 0. So I have a first order differential equation with constant coefficients. So I can solve this using the methods that we spoke about in previous videos. Let's use separation of variables for this one. So I will have 10I is equal to di dt, multiply everything by dt. Sorry, I should have a negative here. Negative 10I equals di dt. So negative 10I dt is equal to, I'll bring the I over as well, negative 10 dt is a 1 over I di, integrating both sides on that. I will have negative 10t plus a constant of integration is equal to natural logarithm of I. Taking the exponential of both sides is going to give me this, that I of t is equal to e to the minus 10t times e to the c. And I can kind of simplify my arbitrary constant of integration and introduce a new variable, let's just call it a, which is e to the minus 10 times e to the minus 10t. Next, I need to find what's my constant of integration. So use the initial condition, which was 4 amps. I know it is 4 amps. So use the initial condition, which was I of naught is equal to 4 amps. So substitute the time is 0 and I equals 4 into that equation. So I will get 4 is equal to A times e to the 0, which is just A. And so therefore I have that my current in my inductor is 4 times e to the minus 10t, and this is units of amps on that one. Okay, so let's pause for a moment, remind ourselves what it was that we were doing. So we're analyzing this circuit here and we're trying to find the voltage, but what we actually did was find the current. So I need to do a little bit more work to actually get the voltage on the inductor. So for this I go back to my definition of an inductor, or my equation that describes an inductor. So let's make a note about this. So need to find the voltage on the inductor. Okay, so I have voltage on the inductor is L di dt. So our inductance was 0.32 henries times the derivative of times basically derivative of I of t. So let's work what that will be. So I'll have the 4, I'll have minus 10 times e to the minus 10t, and we can clean up our numbers a little bit. So 0.32 times 4 times 10 is negative 12.8 e to the minus 10t. And this one has units of volts. That's the voltage on the inductor, but the question asked us for the voltage on the 10 ohm resistor over here. So I need to use a voltage divider, basically this network here. I know the voltage at the top, I know VL, so I can use a voltage divider. So let's do that. I'll just copy this circuit down again. When I'm doing it here on a computer, you know, it's a little bit harder to see all of the things at once, so I'll just copy it down again so that you can see what I'm doing. We have here by voltage division, we have the out is the voltage on the inductor multiplied by the voltage across which we measure the output. That was 10, divide through by the total, so 10 plus 6. So that will be, I'll just combine all of these numbers together, so that's 10 divided by 16, so it is 0.625 times VL. Let's sub in what we know about VL. So VL from above, I'll just write this out with a multiply sign to make it clear. From above, VL is negative 12.8 e to the minus 10t. And we can combine our numbers. So that's 12.8 times 0.625 is minus 8 e to the minus 10t. And that one has units of volts. So that one is our kind of final answer for part A of this question, which was to find the voltage. All right, let's go back and have a look at what we needed to do for part B of this question. So part B says, what proportion of the energy that was stored in the inductor is dissipated over here in this 4 ohm resistor? So in order to do that, we previously discussed our strategy. So we're going to find the initial energy in the inductor. We're going to find the power that gets dissipated in the resistor. and then convert that power into energy by integrating and then find the ratio, so what proportion of the total. So let's work through that particular part of this question here. So part B, initial inductor energy. So energy in the inductor is 1/2 Li squared. So that is 1/2 times 0.32 henries times the initial current was 4 amps. So times 4 squared, I squared. So that is, again, bear with me, 132 times 4 squared, that is 2.56, and that's in joules. So SI unit for energy is joules. So that's the energy in the inductor. That's the total amount of energy that we have in this circuit once the switch has moved to its other position. Now we want to know of that energy, how much of it ends up here in this 4 ohm resistor. Now what we need is to find the power in the resistor first of all. So the power at the 4 ohm resistor is, I'm going to call it P4 ohms. That power will be V squared over R, so voltage squared divided R. Now the voltage across this resistor, because I have my reference node here and I have this node voltage VL, the voltage on that resistor is just VL, which I actually calculated already to be this value here. So I can actually substitute that directly into my equation here. So that was negative 12.8 e to the minus 10 t, all of that squared, divided by the resistance is 4 ohms. So let's calculate 12.8 squared divided 4 gives me a number at the front is 40.96, and then I have a squared on that exponential, so that will be e to the minus 20t. So when you square the exponential, you multiply those numbers together. So it's e to the minus 20t. So that's the power in that resistor as a function of time. But the question asks us for the total amount of energy that actually will be dissipated there. So the total energy is, let's call it energy of 4 ohm resistor. So energy in the 4 ohm resistor will be the integral over all time, so integral from 0 to infinity, of the power with respect to time. So that will be integral 0 to infinity of 40.96 times e to the minus 20t dt. And if I evaluate that, I will get 40.96 divided by negative 20 e to the negative 20t, taken over my limits of integration, which go from infinity to 0. So the number at the front, 40.96 divide negative 20, is going to be negative 2.048. And then my substituting my limits of integration, so e to the negative infinity is just going to give me a 0, minus in e to the 0 is just going to give me a 1. So I will end up with 2.048 joules of energy. All right, we're nearly there. So therefore the proportion dissipated here is, so it was 2.048
divided by the total energy that we had in the inductor was 2.56 joules. So that number is 0.8. So what that means is, so therefore 80% of the energy in the inductor will dissipate in the 4 ohm resistor. And that's the final thing that we needed to calculate for this question.